Hi all, this is Mr. Yeager for chemistry. We are moving into understanding solubility. This is a big part. It's a good analysis part of, do we really understand what's going on with some solutions? We're getting into much more of the analytical phase of this unit as we begin to calculate stuff. After this video, we're not doing a lot of calculations on this, but we will be interpreting what are called solubility curves and graphs so that we understand how much is dissolved, being able to describe the solution, being able to identify whether it's a solid or a gas being dissolved, a number of things that can be done with this. So rather than a lot of terminology and matching, that we've done so far, this is finally a bit more analytical and application based of the unit. Again, this presentation was made by another excellent chemistry teacher, and here we go. So, a little bit of review first. We know solution is a homogeneous mixture. Again, it all looks like one entire substance, but it is a mixture of two or more objects, two or more pure substances put together, but keeping their individual properties. It is made up of a solute and a solvent. Again, solute is dissolved in solvent. We are primarily playing around with the solute part of it on the graphs that we'll be doing, but I'll show you one thing that could happen with the solvent. And so that leads us to already this newer term, solubility. So solubility is a measurement, okay? This would be a physical property that can be adjusted based on the amount of stuff, but it is a physical property of a compound or an element, okay? And it describes how well you can dissolve that substance in a particular solvent at a specific temperature. So it tells you how much can be dissolved at a particular temperature. Those are kind of the two main things I want you to focus on. Now, one other thing that we do need to kind of make sure we understand, this is measured based on a certain amount of solvent. So it says it's usually measured based on 100 grams of solvent, all right? That is what we can possibly manipulate, and I'll show you how, because if you have more solvent, obviously you can have more solute, but it doesn't necessarily change the solubility. A solubility is essentially like a fraction or a proportion based on how much solvent is there, okay? And it is unique to pretty much every single substance, okay, for different temperatures. Now, some terms that again go along with this, all right? You probably have heard me already say these terms. We have what's called soluble and insoluble. Soluble basically means that the substance can be dissolved, okay? It is like dissolves like. If you go back to the idea of polarity, it very likely means that you have a polar substance and a polar solute and a polar solvent. Insoluble means it would not be dissolved. Solubility curves looks at soluble substances until they're not anymore. Until you cannot dissolve anymore in it, okay? So it would be that they could still be dissolved, but we'd have to adjust the temperature. I'm going to leave this up if you're interested in this. This is kind of some application of why we do care about solubility, okay? But we don't include this in our notes, at least where I teach. But it is good information in terms of understanding water quality, okay? When you do get older, you do get sent these water quality reports from your local water department to let you know how they're doing with making sure that the cleaning water is safe to drink, okay? So if you want to pause at any point, you can pause it and be like, let me read through this, okay? Same thing with these next slides. You can see what they test for, all right? And they make sure that everything is no in terms of the amount that's left that's in it, okay? You've heard maybe of some news reports where, unfortunately, things like lead was very high in some people's drinking water in the U.S., and that could lead to major issues. All right, getting back to what is on notes and very important that we do assess on. We are interested in what can affect solubility, okay? So there are some things that we can do to try to either speed up solubility, okay? I want to be clear about this, speed up solubility. Only one of these things actually changes solubility, and that is the temperature, okay? So all of these things can affect how quickly or not quickly you get things to dissolve, but only temperature actually will change how much you can dissolve. So temperature, higher temperature dissolves faster for solids and liquids. That means for gases, if you increase temp, you decrease solubility of gases. All right, that's going to be important to realize. So for solids and liquids, if I increase temperature, increase temp, increase solubility. All right. For gases, if I increase temp, I decrease solubility. That's because gases are harder to trap. If you increase the temperature, you're making them move faster and they can escape. Okay, is what we're saying. Agitation and stirring. If you stir, it'll dissolve faster. That's because you're making them, in order to dissolve, we're looking for the solvent to surround the solute. So if you stir it, you're allowing them to interact and to obviously surround it. Surface area. If you crush up what you're trying to dissolve, it will dissolve faster because it can be more easily surrounded. So this would be the idea of like taking a pill, like for medicinal reasons. All right, you take a little pill. What happens is it doesn't immediately dissolve, and you either have to get through that casing to try to first dissolve it, but then usually there's a powder inside of it. But if you have just an aspirin that's a pill, what's going to happen is it's only going to dissolve the outer layer. But if you crush the aspirin, you can then go ahead and take it, and it should more quickly dissolve into your bloodstream. Okay. Pressure only affects gases. If you increase pressure, you can dissolve something faster because you're kind of forcing it into the solution. Think of carbonation here. We carbonate things and then seal it very quickly so it has a very high pressure, and all that carbon dioxide dissolves into the soda, which then obviously helps keep it in the soda and keep the taste. That's why when you release it, you do release quite a bit of the carbon dioxide. It does come out, but then still there's quite a bit trapped in the soda. So one more time, I will say this: if you increase all of these, you increase solubility. That's the nice thing. The direct relation is if you increase all of these, you increase solubility. The only thing you have to pay attention to is temperature is opposite for gases, and pressure only works on gases. We talked about this term. Saturated means that we have a maximum amount dissolved. We're reviewing this because we're going to use this term to describe certain situations on the solubility curves. Unsaturated means that you use less than the amount that can be dissolved, so that in other words, we can still dissolve more. Okay, we have not reached solubility. And then supersaturated means we are above what should be dissolved based on that temperature, but it is actually still dissolved. Again, guys, this is very, very rare. This is very difficult to do. I have not made many supersaturated solutions because they are very particular, and it does depend on what you're trying to use. So it's not just, oh, I added more than there should be, it's supersaturated. No. Most of that solute will settle to the bottom, and therefore you just have a saturated solution with a bunch of solute on the bottom that's not dissolved. All right, so the main thing on this part is a solubility curve. Okay, and so there's a few things we need to really try to understand on solubility curves. So first off, what are we seeing? On a solubility curve, you can see that we have temperature on the x-axis and grams of solute dissolved in 100 milliliters of water, or 100 grams of water, on the y-axis. So temperature on the horizontal, how much is dissolved on the y-axis. Okay? The first thing I basically just want to make sure we can understand, and one of the things you could be asked for on this, and we'll use this very simple one, you can see it has two substances on it, would be very simply that I could say, all right, at 40 degrees, how much sugar is dissolved? So you go from 40 up to the sugar line, and then you go over and you go, what, 230 grams. Obviously there'd be some sort of estimation there because it's somewhere between 200 and 250. Okay, it looks like it's a little bit closer to 250. That's why I said 230. So the line itself is telling you how much can be dissolved, all right, at the different temperatures. And you can see the line is going up as temperature increases. That's what we said. In general, for solids, if I increase temperature, I will increase solubility. I said that on the prior slide. Okay? So the line itself is telling you how much it will dissolve. All right? 2. Well, I'll wait on this. Maybe there's another slide with this. Sorry. Okay. So that's the first thing I want to say. If we do see a line going down, I'm going to bring up another solubility curve. That means that that is most likely a gas. So if the line is going up, it's a solid. If the line is going down, it's a gas. Now, we are giving you salt right here. As you can see, with table salt, it barely changes at all. Okay, it's basically, it is going up, like the line's ever so slightly going up, but so it is a solid, but salt really doesn't change its solubility too much. All right, so as I said, the line created represents a saturated solution. So that means if you are on that line, it is a saturated solution. Anything that is above the line, if I give you a data point and it goes above the substance you're looking at, we're going to call that a supersaturated solution. If it falls below that, it's an unsaturated solution. Okay? So, what is the solubility at 20 degrees? We would sit here and go, I kind of was already doing this, for sugar, 20 degrees going up, it's 200 grams. Okay? So that would be it. And that would be a saturated solution of sugar because you're on the line. All right? Is the solution of salt containing 100 grams of solute at 40 degrees saturated, unsaturated, supersaturated? So here are the first kind of, I would say, more simple questions we would give you to try to analyze this graph. So it says at 40 degrees, you put 100 grams in. And we say it's actually dissolved. It probably won't, but we're going to say it is. So you are above the line, which means you are supersaturated. I always tell people, you're flying above the line like Superman, it must be supersaturated. If you're under the line, you're unsaturated. I mean, it's not that difficult to remember each of those things. If you're on the line, it's saturated. All right? Is sugar solution containing 150 grams of solute at 60 degrees saturated, unsaturated, or supersaturated? Again, you can take a moment to look yourself. 60 degrees, 150 grams. Well, I'm well under the line. Okay, and I have to look at 60 degrees. I'm well under the line. That would be unsaturated. Okay? Is a salt solution containing 48 grams of solute at 80 degrees saturated, unsaturated, supersaturated? All right. 80 degrees, salt. 80 degrees, 48. I mean, and this is where you don't want to get too technical with it. You're basically drawing a dot right here. If your dot touches the line, you're saturated. So this would be a saturated solution. This says supersaturated, I disagree. Okay? It is saturated. So this is not meant to be, if you're drawing that line and draw a nice dot and it basically touches it, you are a saturated solution. I don't want you to sit there and try to be putting this under a microscope and trying to go, wait, is that line above, below, or on it? We try to give you some easy questions where it's like, that is very clearly above, that is very clearly below, that looks like it's basically close enough, so I'm going to call that saturated. Okay? All right, some other questions you can get. Which solute is most soluble at 70 degrees? Well, whichever line is higher is more soluble. Okay? So we would, if you have multiple lines, whichever one is higher at 70 degrees. So at 70 degrees, I mean, you could get numbers for it. Basically, salt's still at 48, but look, sugar can dissolve almost 320, 15, something like that. So clearly sugar, because the line's way higher. Okay? Which solute is least soluble at 30 degrees? I'm already going to say it's salt. Okay? We know that because it's lower. All right? Some other ones that we can do. Okay? It's more likely you're going to get one that looks like this on any sort of assignment, okay, that you have lots of lines on it. And this just, students get a little scared by it. I can understand there's a lot of stuff to look at, but you just need to focus, okay? When you read a problem, identify specifically which chemical the problem is mentioning. So if it says, hey, what is the temperature, how much is dissolved of NaNO3? So now I'm only looking at the NaNO3 line. I could care less what anything else is doing. Focus on just that line. Okay? A common question that you could get is something like, what two substances have the same solubility at, let's say, 28 degrees, like this one right here? Okay? What two substances have the same solubility? If I'm looking for the same solubility, I'm looking for when the curves overlap. So I would go up and be like, where do I have curves overlap? There's some closeness right there, but that's not what I'm looking for. I'm basically looking at this one. Okay? So that would be, I need to figure that out, that would be NH3, and then this line, which it doesn't mention what it is until up there, KNO3. So at 28 degrees, KNO3 and NH3 have the same solubility. Okay? Other questions you can get that really don't involve too much thinking. I could ask, which substance is changing the most? Well, if I'm changing the most, that means it's curving the most. So that would probably be KNO3, because look, it starts all the way down here and ends up here. That is the largest change of anything. We already said which one changes the least. That would be NaCl. This is an example where I say, what is a gas? Can you identify any gases on this? You would look for things that are going downward. So NH3 very well could be a gas. SO2 could be a gas. All right? It even has HCl. I mean, HCl can be a gas. It could be a liquid, okay? But it could be a gas. All right? So those are just different examples. Other possibilities, I don't think you're going to, I mean, this is maybe getting a little bit advanced. Other possibilities that we could do, and I'm going to just show one example of each of these because I don't think you're going to really have to hammer this too much, is I can adjust the amount of solvent. So all of these solubilities are based on 100 grams of water. All right? So if I said, I'll try to choose something simple here that I can try to find. Let's use KNO3. At 60 degrees, KNO3 basically has 110 grams dissolved. So at 60 degrees Celsius, KNO3 can have 110 grams dissolved in 100 grams of water. If I said, well, at the same temperature, 60 degrees, how much KNO3 can be dissolved if I have 200 grams of water? Well, what am I doing? I'm doubling the amount of water that's available. I know how much can be dissolved at 110. I'm doubling the amount of water, so what am I going to do with the amount of solute that can be dissolved? I double it. So I could have 220 grams of KNO3 dissolved if I have 200 grams of H2O. All right? That would be how we would maybe make this a little bit more difficult, okay, is adjusting the amount of water. And if we did that, we would make it very clear. It would be like we double the water, we triple the water, or we would half the water. If I go down to 50 grams of water, I half how much can be dissolved. So it's all proportional, very directly related proportionally. The other possibility would be, and again, I'm trying to find one that I can use pretty easily here. I'm going to use NaNO3. So let's say at 30 degrees, NaNO3, I can dissolve 95 grams. At 60 degrees, I can dissolve 125 grams. So, what I could ask is I say, I make a saturated solution of NaNO3 at 60 degrees Celsius. A saturated solution of NaNO3 at 60 degrees, I can get 125 grams in it. That's what the graph is telling me. I then lower the temperature to 30 degrees Celsius. If I lower the temperature at 30 degrees, only 95 grams can be dissolved. So my question is, how much NaNO3 precipitated out of solution? I sometimes say crystallized out of solution. What I'm basically looking for here is what's the difference between 125 and 95. 125 minus 95 is 30 grams. 30 grams of NaNO3 would come out of solution. It would settle at the bottom. So what I'd have is I'd have this solution where I'd have all the NaNO3 all dissolved, but if I lower the temp, all of a sudden I'll see some of that stuff settle down to the bottom, and I would see it on the bottom now. It would not stay dissolved. All right? So that is another type of question that does possibly happen, okay? It might be a little advanced. We might not be doing that at on level, but it's worth still seeing it, okay? Is to kind of just go, how much more can I add? How much comes out? And what you do there is you get 2 data points and just subtract the amounts. All right? So that's everything with solubility. All right, thank you.